So this video is about conservation of energy. Okay, so we talk about mechanical energy, right? There are two kinds of energy we mentioned. One is gravitational potential energy, the other one is kinetic energy. But the conservation of energy, as you can see from the slide here, it talks about energy cannot be created or destroyed. Okay, it may be transformed from one form into another, but the total amount of energy never changes. Okay, so what do we mean by that? That means that energy is always, conserved. Okay, but it could happen that one type of energy will be transformed to another type of energy, but total amount of energy is always conserved. Okay, so in our class here, okay, as you can see, I can show you some of the examples here. This, for instance, if you lift something very high, okay, let's say I lift this marker very high, so basically I'm storing the energy through the potential energy, right? So the potential energy is, we have the potential energy. Once I release it, okay, the potential energy actually becomes what? Kinetic energy, okay? So the potential energy is decreasing, but the kinetic energy is getting bigger and bigger. Okay. Okay, and also, if you have system of bow and arrow, so when we draw the bow, we do work on the system and then give its potential. So the work is the ability to give to change the energy or to transfer the energy. When the bowstring is released, okay, most of the potential energy is transferred to the arrow as kinetic energy. So some of the potential energy is converted to kinetic energy, and then also as well as heat. But the total amount of energy is still the same. Okay. I can give you some more examples about conservation of energy. Okay, so for instance, the one I just gave to you, you have a free fall, right? If you have a free fall motion, so we have potential energy, kinetic energy is 0 here. So if you have a free fall, okay, so we have potential energy, kinetic energy is 0. This is H, so equals mgh. This is my reference point. But now once I release it, okay, before it hits the ground, okay, I draw the ball here, then the potential energy becomes 0 because the height now is 0. But the kinetic energy here, so we say this initial, final, kinetic energy is 1/2 mv squared. So, but in this case, actually, the mechanical energy is conserved. So which means that, okay, so initial kinetic energy plus initial potential energy equals final potential energy plus kinetic final. So in this particular case, okay, so we say that, okay, initially this is the total mechanical energy. Mechanical energy equals potential energy plus kinetic energy. Okay, that's the initial case. The final case is potential energy plus kinetic energy as well at the final position. Okay, so for this we call mechanical energy conservation. Mechanical energy conservation. So there's no other energy involved in this case. Okay, so this is what we do. Potential energy initial, kinetic energy initial equals potential energy final plus kinetic energy final. Okay, so which means that if I plug the numbers in here, so mgh plus 0 equals 0 plus 1/2 mv squared. So we have mgh equals 1/2 mv squared. So this equation tells you that the total potential energy actually is converted to all to the kinetic energy. So during this process here, okay, so the potential energy initially has maximum. Kinetic energy is 0. But once the ball is moving down, so potential energy is converting to kinetic energy. That's potential is getting smaller and smaller, but the kinetic energy is getting bigger and bigger. Eventually, the final position here is all converted to kinetic energy. Okay, so for this conservation of energy principle, especially for our class, we're going to focus on conservation of mechanical energy. Okay, so the nice thing about this, again, both potential energy and kinetic energy, they are scalars, so you don't have to worry about directions. The second thing here is, when we use this mechanical energy conservation principle, all we care about is the initial and final position. I don't care about the middle process. Okay, so all I need to ask yourself when you do this kind of problem is, what is the initial potential energy and kinetic energy? What is the final potential energy, kinetic energy? And I don't have to care about what is in between. If you look at this final equation over here, okay, so you can see actually the masses cancel out. I'm going to redo this. So it's mgh equals 1/2 mv squared. So if you look at this, mass is the same. I can cancel it. gh equals 1/2 v squared. So in other words, if I drop the different objects, okay, the mass is different. Actually, it doesn't matter, okay, because mass is irrelevant here in this situation. Okay. The second thing I want to talk about is the comparison between the kinetic energy and momentum. So I'm going to do another video